So before I start, I guess I want to share some anecdotes on how I got to know Mignon, since that's the first conference I can afford that luxury. So during my PhD, I was writing some, so I was working on the embedding problem and obstructions to it with Thomas Schlank. And to do this, we needed to compute something in the étale commutative number fields. And we managed to do so. And then around the same time, Mignon posted his papers on arithmetic transcendence theory. And I read the papers and I saw that, what Tomer and I had really had some connections to what Mignon was doing. So what he computed some arithmetic action functionals without knowing it. So I was quite happy about that. And then the time for my defense came around. And for your defense in Sweden, you're supposed to choose an opponent. And the opponent, he has two objectives. So first, he's supposed to give a presentation of your work to the audience. And second, the opponent's supposed to ask questions about your work. So when time came around, I suggested to my advisor that we should pick Mignon as my opponent. I did not expect him to accept, but to my surprise, he did accept. So I hadn't really no connections to number theory, arithmetic geometry back then. My advisor was in homotopy theory. So I was surprised, but happy, but also nervous. So then came the time of my defense. And then, as you see here, Mignon is presenting the work of Carlson. I was a PhD student. So if you ever had like the opportunity to have Mignon present your work, I would really urge you to take the opportunity. It's a real luxury to have Mignon present your work. It was kind of fun as a PhD student to have him present your work. So yeah, this was the first time I met Mignon. I guess three things struck me regarding Mignon. So first, he was very passionate about sharing his knowledge to people and really sharing his ideas. So for example, he took quite a lot of time in trying to explain étale homotopy theory to my parents using this picture. So this is the Swan by Hilma Flint. So yeah, this was like a public presentation. This was one of the examples he used to explain étale homotopy theory. Maybe Mignon could tell you more about this later. So my parents really appreciated the gesture, and yeah, it was very nice. And then what really also struck me was that he was intensely curious. Usually, and PhD defense in Sweden is around 90 minutes to 2 hours. I think my PhD defense was well over 3 hours, almost 4 hours. And this was due to, so my thesis had 4 papers, and one paper was quite technical, and I really thought no one would care. And I didn't also prepare for questions on this paper. But Mignon really focused on this paper. So, and he kept on asking questions and questions about this paper for quite some time. And yeah, and it was not for putting me on the spot. I really felt it was genuinely curious and wanted to understand the material in there. So yeah, and it was wonderful, really. And even after my defense, one of the retired professors said, well, it was a great defense, but man, this opponent, he was really quite curious. It should make not ask so many questions. And lastly, what also struck me was that Mignon is very knowledgeable in many subjects. So during the defense dinner, Mignon and I, we sat at the same table. And during the evening, we discussed quite a bit. And he had taught me quite a lot during the evening and told me about different subjects. And I thought, well, there might be one thing I can teach Mignon, one subject where I can share some new information with him. So I was pondering what could that be. And I thought, well, I mean, I've read quite a bit, so maybe literature is something I could found something new. And to make my chances even better, let's take Swedish literature. So I was asking Mignon, well, have you happened to heard about the playwright August Strindberg? So this famous Swedish playwright, and it quickly became clear that Mignon had read very much of August Strindberg and knew much more than I did about August Strindberg. So after that, I gave up and sort of this enterprise of trying to explain. So, and after that, we kept in contact, and Mignon really was always very generous to me and invited me to work with him on projects and helped me both mathematically and personally in some aspects. And I don't think I would be doing the math I'm doing today if it wasn't for Mignon. So I mean, I would like to thank Mignon for like sharing your knowledge and your being kind and your generosity. I think I can say it for all of us. So thank you and happy birthday. Right. So now to my talk. So I will be speaking about joint work with two. So this is based on two separate papers. So one of the papers is with Jakob Stix. One of the papers is with Peter Hain and Sebastian Wolf. So I will speak about, the title of my talk is, as already said, that the étale topos reconstruct varieties over, I will write many fields, and what many is, I will sort of soon describe. Okay. So I'm going to start with a very naive question. So let K be a field, and suppose I have a variety X over K. So my first question is then, if you give me the étale topos of X over the base étale topos, can I determine X over K? So this is a quite naive question. So clearly there must be some restrictions on this. It seems to be a very general thing, and we shouldn't expect this to hold in general. So for example, one thing we must restrict, restriction on base field. So for this kind of question to hold, we must put some restriction on X. So for example, if K is equal to the complex numbers, any two curves, two smooth projective curves of same genus. Can you see what I write, by the way? Have equivalent étale topos. Okay, so we can't expect this to hold in general. What are there any more restrictions? Well, yes. So for example, for any scheme X, I can take the reduced closed subscheme. This will always induce an isomorphism on étale topos. So if X is not reduced, I have no chance of being able to reconstruct X from its étale topos. And also, I mean, like if you think like I could take the cuspidal cubic, I can take its normalization like this. So this induces iso on étale topos. So I must somehow restrict the singularities I allow my variety X. And also there's like counterexamples coming from the Frobenius. So for example, if K has some positive characteristic, I can consider my structure map over K. I can consider also my structure map by a composed of the Frobenius, and they will have an equivalent étale topos over spec K. Isomorph is simply being given by the Frobenius. So you see, there's no way this question holds in general. There are lots of obstructions I must take into account. So the answer is then no to this. So we must try again. So let's try to take these obstructions into account and see what we can then come up with. So this, if you look at this example here, this is a universal homomorphism. There's a theorem that universal homomorphisms induces equivalences on étale topos. This is also universal homomorphism. So and also this guy here is also universal homomorphism. So it seems then, well, let's try to invert universal homomorphisms. Maybe the theorem is true then. So here's a better question. Also, like, I guess asking determine X over K is not really well defined. What do I mean by that? Let's make that more precise. So here's a better question to ask. Let K be a field, and let us denote by scheme K. This is the category of schemes of finite type over K. And let UH be the universal homomorphisms. Then the better question to ask, which is more well defined and which have a more chance of being true, is the question whether the functor going from the category of schemes of finite type, localized at the universal homomorphisms, into the category of topoi over the étale topos. Is this functor fully effective? Is the question clear, what I'm asking?
What is a universal homomorphism?
So it's a homomorphism which is stable under base change. So it's a universal, so it's stable, yes, it's still a homomorphism. You have to take every fiber product.
Arbitrary base change.
Arbitrary base change, yes. So this was asked by Grothendieck through Faltings when K is finitely generated over Q. So now we have a better question, and we really think this ought to be true, but it turns out that no. So that was my talk. Thank you so much. No, no. So there are some further obstructions to take into account. There's a fact which I will use to explain what the obstruction is to make this true. So given any topos X, there's a recipe for spitting out a logical space out of this topos. And this is, you do this by considering the sub-objects of the final object. And this is then a frame, which is sort of like an abstraction of the notion of a topological, like the set of opens of a topological space. And then you can do some more work and get an honest topological space out of it. So to a topos, I have a recipe for spitting out a topological space. And this is functorial. So if I have a geometric morphism between topoi, this induces a continuous map on topological spaces. And lastly, to make ourselves feel maybe more at ease with this construction, is that if I have the étale topos of a scheme, then this recipe spits out the Zariski topological space of X. So if you don't mind like this abstract thing, you can just think it's a recipe for spitting out this Zariski topological space when X is the étale topo of a scheme.
Can you remind us of what that is?
What
This Zariski topological space.
So just like you have a scheme, I can look, it has a topology, right? The Zariski topology. That's all I'm saying.
Okay.
So like I have like these affine opens, and then I have the Zariski topology on these. Then I glue the top, then I get the topology from that. It's the usual topology you have in a scheme. So here's the obstruction for why this theorem was not true. So suppose now the K is a field of characteristic 0, and you take, this is the Laurent series in T. So you can pick a section of this map of Galois groups, the Galois group of the Laurent series in T, to the UK. And by working with Galois categories, you can see that this will induce a map from the étale topos of such a section will give a map from the étale topos of spec K to the étale topos of this Laurent series. And then what you can do is you can take first A1, you can map it down by the structure map to the base field. Then I can use my sort of like hospital section or what you would call it to get a map to the étale topos here. And then now this map here is induced by a map of schemes. I complete at at 0, and then I take like the inclusion to the generic point. If I consider the map of topological spaces here, this has the property. So for example, everything here goes to a single point. Everything here still goes to a single point because the topological space is associated to these top areas points. So this is also a point. And now this thing here takes the point to the generic point. So now I have a strange map of topoi, which takes every closed point to the generic point. And for maps of schemes, this will never happen. So something must be done to fix this. Is this construction somewhat clear? Okay, so we must put some restriction on the map of topoi for this theorem to be true. So here's the fix then. So let R top pin, there will be the category with objects topoi over the étale topos of K. And now I restrict the morphisms in my category. The morphisms are what I call pin geometric morphisms. Those are geometric morphisms which takes closed points to closed points under this associated realization of topological spaces. So now the correct question to ask, and which has a chance of finally being true, is the following. So if I have a field K and have the schemes, category of schemes of finite type over K, and UH are the universal homomorphisms, then the question is, whether the natural functor from the category of schemes localize the universal homomorphisms to the category of pinned geometric like the category of top over K with pinned geometric morphisms. Whether this functor can be fully faithful. So this is the question we will focus on. And this was not the original question you asked, but it seems to be something you must take into account for it to be true. There might be other ways to fix it, but I will not. Any questions?
I guess the finite type is what gives you the pinned thing, I guess. Is that right?
Yeah, exactly. I used for finiteness, I used the pinned. And I must also take some conditions on finiteness for this to be true. Because otherwise I can do like separable closed fields and they would have the equivalent to top. Yes, I'm using the finite type for this pinned to make sense. I'm using like Chevalier's theorem somehow. Okay, so this is what we'll try to understand. And it turns out that the answer to this is positive in many situations. So the first is a theorem with Peter Hain and Sebastian Wolf, where we show that the answer to this theorem is true if K is finitely generated over characteristic 0, or if it's finitely generated positive characteristic, but we require that the transcendence degree is at least 1. Under these assumptions, this functor here is fully faithful. And I should add that work on this had been done previously by Voevodsky. So he proved this for normal schemes. Like if I instead consider the category of normal schemes and the category of pinned morphisms, then he showed that the functor was faithful. And this is used as input in this proof. But to get the theorem for all schemes of finite type, you have to work a bit. Okay, so this is nice, I guess. But then you can also, can you generalize this further? And this is I did with Jakob Schmitz. So this tells us that, well, the theorem is also true if I consider sub-p-adic fields. So if the theorem is true for sub-p-adic fields. So if K is a sub-p-adic field, and sub-p-adic means this is a subfield of a finite generic extension of QP and prime P, then this functor is also true. So in particular, this recovers the results of this in characteristic 0. And without using Voevodsky in any way. Okay. So the plan now for me is I'm trying to explain how this proof goes, what goes into that. And on the way, I will also then explain some aspects of the proof of this, because some of the reduction techniques needed for this is also present here. Okay. Right, so this is what I'm. So, by the way, feel free to interrupt me at any time.
So I'm curious. So over C, so we don't know it yet.
Over spec Z? Or
Yeah, spec C.
spec Z. So, I mean, that's a very good question. We don't know it yet, but as you have good hopes to believe that something like it should be true.
But then how was that problem addressed? Yeah,
You mean over spec Z? Or
spec C.
over spec C? You know, we don't. I don't. Which is false over spec C.
So if we don't. So the conjecture was only for finite agents.
So I mean, I guess that you can like also for what base fields can this be true?
Right.
Yeah. So this is an example showing that for the complex numbers we have no chance of it being true.
So the conjecture was. So what was the condition on the base field in the?
I would say we're not entirely sure what conditions to put on the base field yet. But it seems
It's part of the question.
Yeah, it's part of the question. For what fields can this be true? And for the complex numbers, it's not true. But I mean, you might ask, what about, I don't know, algebraic closed fields characteristic P? I don't think it's clear that it's false there.
What about over finite fields?
Over finite, that's a very good question. So I've been trying to work over finite fields, but it's open. And also, I think the questions over spec set, the integers, something that makes sense and would be the ultimate goal, sort of this with this project. So thank you. Further questions?
If you like compose this functor with the inclusion of the pin,
Yes.
is this going to be conservative? Or are there, you know, isomorphisms that are not pinned?
That's a good question. No, I think you're fine then. If you're,
Will still be conservative.
Yeah. Yeah. Okay. So here's the plan. I'm going to do this. So as I said, we'll skip prove this for normal schemes. This thing here. And before I start, I want to like give a slogan for what we're going to call this, like what we're doing here. So if you consider ordinary Abelian geometry, you want to identify some class of Abelian schemes for which pi1 should be fully faithful. And in general, this is very, very hard. We don't have a good description of Abelian varieties or a good field, or say of finite generator characteristic 0. We only know what the one-dimensional Abelian varieties should be. They should be hyperbolic curves, and the examples built from them by vibrations or something like that. So in contrast, in this, what I would call topos theoretic Abelian geometry, and if you have a good base field, all the varieties are Abelian in this sense, in this generalized sense. So you don't need to care about characterizing what the class of Abelian variety, what that is. Everything is Abelian in a topos theoretic sense. And I think it makes sense to say that it's like this topos theoretic Abelian geometry is some sort of like Abelian paradise where things you hope to be true in essence are true. So it's quite a nice dream world to be in at times. So here's what we're going to do to prove the theorem. So first, this category is horrible. We don't want to work with that. I mean, it's like a zigzag generally. We're localizing universal homomorphisms. Morphisms are like zigzags that look horrible. We don't want to work with that. So we're going to replace that category. So first, we replace this category with some category you can really work with. That's the first step. Step 2 is a further reduction step that shows that to prove that the functor in question is fully faithful is enough to prove that the functor from x to a1 to the corresponding things which are pinned, that this map is bijective when x is smooth and affine. And these two steps are with Hein and Wolf. So with this, it seems more doable in some sense. Now we're in the realm of, it feels very close to Abelian geometry. And then step 3 is that we will use Abelian techniques to prove the bijectivity in step 2. So that's the plan. We're reducing the base category, reducing to x smooth and affine, and y equal to affine y. That's the plan. Any questions? Yep. So first to replace the category, I'm going to define semi-normal rings. So this was known, by the way, to Grothendieck for quite a long time. So a ring A is semi-normal if for all x and y in A, x cubed is equal to y cubed, x squared is equal to y cubed. If you have such an equality, there is an A in A, such that x is equal to a cubed and y is a squared. So these kind of things, that's not semi-normal. And the scheme X is semi-normal if for any affine open, the ring of like functions on that open is a semi-normal ring. So why do I introduce this? Well, this is because of the following effect. So suppose that K is characteristic 0. Then you can show that any universal homomorphism between semi-normal schemes is an isomorphism. And further, the inclusion in the category of semi-normal schemes, in the category of schemes, has a right adjoint, the semi-normalization. And the co-unit from the semi-normalization to X is a universal homomorphism. And further, this right adjoint here gives an equivalence between the category of semi-normal schemes of finite type and the localization of the category finite type schemes of the universal homomorphisms. So we can replace this ugly category, this category, which is much easier to work with. Yes?
So when you mentioned Voevodsky's theorem, it was for normal schemes.
Yes.
I mean, is it going to follow from the end later that same statement is also true for semi-normal schemes?
So we need a descent statement. So we're going to use we're going to use H descent. So the sort of things you satisfy H descent. So that's for that, and so that you can reduce the normal schemes and character for defining general cases.
Sorry, just to make sure I understand, does this mean that like hom from spec K to X doesn't change when you invert the universal homeomorphisms?
So you mean in what sense? I mean,
Homs from spec K to X, like the rational point of X, survive the localization, I guess, right?
right? Yes. Yeah.
Nothing
Yeah.
changes.
No. Yeah, because the universal yes, that's fine. Yeah. So replacing this category with this. And in characteristic P, you can describe this category here in terms of like the perfection of these one category, but it will not be important to us. So now we sort of like replace this category with this. So the next step is we're still assuming case characteristic 0. Then we can reduce to showing that this functor here is fully faithful if only if the functor, this map from the semi-normalization of X to Y to the pinned maps between X semi-normalization and Y is bijective for all X and Y functions. So now I don't need to care about zigzags anymore. I can just use like honest homomorphism of schemes. And then step 2, so you can show that these functors, homomorphisms from K to Y, and then I have in the first variable have the semi-normalization of the first argument. And also the corresponding thing for pinned, you can show that these two functors satisfy H descent. So this is, I mean, there's some things going on into this, but I mean, I'm not going to explain how to prove it. But they satisfy H descent. And then you can use standard arguments using resolution of singularities and all these things are available to you when you have H descent. To show that it's enough to show that this map here is bijective when X is smooth, connected and affine. Yes?
Is the semi-normalization of something finite type still finite type?
Yes. That's a good question. But for perfection, it's not true. Then you must work with things that topologically are finite type.
Ah,
Yeah. But if for yeah, so then it's fine.
Are semi-normal rings common?
Yes, I would say. Yeah. That's the definition of common, but yeah.
So you're like just resolving singularities of this type.
Yes.
Did it matter that you picked this particular type of singularity, or like would resolving any if I picked like X to the 5 by cube, picked a different singularity, this whole thing would still go?
I mean, like this part, what I'm doing, I'm really using like all resolution of singularities there. That's to get something smooth.
But in the definition of semi-normal, if I replace like X cubed y squared by some other equation for a singularity and like resolve that,
You mean
would it still be fine?
yeah, I think so. I mean, yeah, if I understand the question correctly, I think that's fine. Yeah. Yes.
I mean, since you're not restricting characteristic 0, when you say resolution of singularities, those could be alterations.
Alterations characteristic P, exactly. So then I get something regular. But I mean, yeah, some characteristics 0. Yeah, further questions? Okay. So now I'm good with, I have, this is a particular much easier example, a much easier thing to prove. So now some facts about the étale topoi, which will be important to us. So if you have a map of étale topoi, from X étale to Y over Y étale, and if it's pinned, i.e. it takes close points to close points, then it has the very nice property that for a finite extension L and a L rational point, I can consider, I mean, I can take this to the maps of an étale topoi. So first I'll take X étale, and take phi. Then it really is a very nice thing that happens is that this map of étale topoi is induced by a map of schemes. So L rational points propagate along is functorially among pin geometric morphisms. From the point of view of Abelian geometry, this is very strong. But it's true. Yep.
Is this more or less a characterization of pin morphisms?
Yes. Yeah.
Why is it true?
I can explain, it would take some time, so I would, happy to, yeah. So from this, so this means that for an finite extension L, I get a map from phi of L from the L rational points of X to the L rational points of Y. And by taking co-limits, I get something from the k-bar value points to the k-bar value points of Y. And the second fact, which you should keep in mind, that if I have a map of étale topoi and some choice of compatible base points, it will give me some map of fundamental groups. These are two things that are good to keep in mind. So now you can show that X is smooth and Y is a finite type, then this map here is always injective. And it's not a hard thing to show. It's using, you can use the L rational points and reduce this to show that it follows. So the really key part is showing that this map is surjective. And it's proven by Vovodsky that for surjectivity, it's enough to show that if you have a pinned map between X and Y, you can construct a map of schemes from F from X to Y, which agrees with phi on k-bar value points. Because I mean, I had a notion, this induced a map on k-bar value points, and this induces a map on k-bar value points. So it makes sense to ask whether these agree. And if they agree, then this map here really realizes this map here. So this was shown by Vovodsky, and what we will use. And you can further assume by some quite elementary argument that Y, in addition to X, is affine. So Y is equal to spec B, and X is equal to spec A. So both are affine. And then, in fact, it's enough to show the statement for when Y is equal to A1. And that's not hard to show, because if you have a map, so say an X and Y are both affine, if I have a map of topoi from X to Y, and have a element B and B, this corresponds to map from Y to A1, right? I can consider composed with phi and then B. If I know the assumption for A1, this will correspond to a map from X to A1. So this gives me a global section of X. Hence, I get a map of sets from B to A. And using very little work, you can show that this is actually a ring homomorphism. So suffices to prove the statement when Y is equal to A1. Is this understandable? So now we've sort of like have a good reduction. So this is the statement we will care about. So case of characteristic 0. Then we have reduced it to showing that to show that this functor here is fully faithful, it is enough to prove that if you have for any smooth geometrically connected affine X, and any pin geometric morphism phi, you find a map of schemes F from X to A1, which agrees with phi on k-bar value points. And in fact, it's enough to prove this for the same statement holds if we replace A1 by n Zariski open of A1. So you only need to prove it from some Zariski open of A1, and then you're done for all schemes. So this is what we're going to prove. And to prove the theorem when case a sub-p-adic field, we will prove that any pinned map from X étale to P1 minus 3 points, that such a map comes from map of schemes and realizes it on k-bar value points. Because if we can do that, we're done by this reduction. Before I go into this is now we finished all the technical steps. Now this is the abelian step we're going to approach. So I think this is a good place to ask questions about the reduction step before moving on. So, questions?
Sorry,
Yeah.
I moved. I had to take a
No,
call.
don't worry.
I missed part of the statement. What have we reduced to now?
We reduced this statement here to proving that this functor is fully faithful, reducing to proving that for any in geometric morphism from X étale to A1, I can find a map of schemes which realizes phi on k-bar value points. This is like the reduction. Okay. So if you see sub-p-adic and you know abelian geometry, your first thing would be to think, well, he's going to use Mochizuki's theorem. And I'm going to use Mochizuki's theorem. So this is a fantastic theorem, Mochizuki, which is, I think, the strongest sort of Hom theorem we have. This tells you if K is a sub-p-adic field, and you have a smooth variety x over K, and y some hyperbolic curve, then the natural map from the set of dominant morphisms between x and y into the set of open homomorphisms between pi1 of x to pi1 of y. This is bijective, and here I need to take conjugation by the geometric fundamental group, but yeah. This map here is bijective. So this is a very strong theorem, and this is what we're going to use. Is this a statement of Mochizuki's theorem clear? But to use this, we have a problem. So if I have something that's pinned, I said that it induces a map on fundamental groups. But why is this necessarily open? It does not follow formally. So this is something we're going to try to show then, that if I have a pinned map like this, then this map is automatically open. Then I can hope to, if this is pinned and non-constant, well, probably maybe this is open. If it's constant, we have no chance, but otherwise it could be open. So we're going to try to show openness of this map then. So to do this, I might skip this slide because I don't think you need to know exactly. So I think you can only need to know the general of this. So suppose that x and y are geometrically connected varieties of finite type over a field K. Then a continuous map from pi1 of x to pi1 of y over GK that is point theoretic, psi serves geometric quasi-sections. If you don't know what geometric quasi-section is, you don't have to worry that much. So you know what a section is, right? It's like a map. This is a section of the projection map from pi1 of x to GK, section of that projection map. A quasi-section is something that's defined a section over some finite GL, some finite extension of L. And so said it means it's geometric, means that the section comes from a geometric point, a rational point, an L rational point. So it's sections over some possibly finite extension of K, which comes from a rational point. And the key property you need to know is that if the map from the K-bar valued points into the set of geometric quasi-sections, if this is injective, given a point theoretic map of fundamental groups, you obtain a map between the K-bar valued points of X to the K-bar valued points of Y. This is all you need to know about like this point theoretic maps. If this map is surjective, then you get an injective. And this holds, for example, if Y is hyperbolic, then this map is always injective over sufficiently nice fields. And a further fact we're going to use that if you have that phi is a pinned map of topoi, then this map here is point theoretic. And further, if this map is injective, then this point theoretic map, this map induced by pi1 on K-bar value points is the same as the map on K-bar value points induced from the perspective of topoi. So we get the same sort of map. So any questions? Is this clear? I guess I'll let silence speak that it's clear then.
Clear.
Is it clear? Okay. So here's the theorem with sticks then. So let K be a Kummer faithful field. So this is a scare word. You don't have to think about it. You can think sub-p-adic field. So if K is a Kummer faithful field of characteristic 0, and if U and V are smooth and geometrically connected curves over K, and V is further hyperbolic, then if you have a map psi from fundamental group of U to fundamental group of V, this is a point theoretic map over GK, then you have a dichotomy. Two things can happen. Either psi is open, or the image of psi is contained in a single decomposition group. In the latter case, the map on K-bar value points must be constant. So this is the dichotomy we're going to use to prove our theorem for the étale topoi. So given this theorem here, I'm going to show how to prove our goal, like using Mochizuki's theorem. Given phi from x étale to p1 minus 3 points, I wish to reconstruct a map F which agrees with phi on k-bar value point. Suppose now that the image of this map of topological spaces is non-constant. I can then pick a curve C, which is nice, geometrically connected, and everything I want, such that this map from C étale to X étale to P1 minus 3 points is non-constant. And by the previous theorem, the map on k-bar value points is not constant here. So it means that this map is open. Previous theorem, because this is pinned. This is an open map. And this means, for weaker reasons, that this map is also open. So by Mochizuki's theorem, I can get a map F, which of course has the same effect as phi star does on pi 1. And this is point theoretic, and F is also point theoretic. I mean, the map on fundamental groups is also point theoretic, and you're done because the map F must coincide with, must be the correct thing on k-bar rational, k-bar points. So this is when the map is non-surjective, non-constant. When this map is constant, it's very like elementary to reconstruct a map, which does the right job. So given this theorem, given the previous theorem, you can prove rule of faithfulness quite easily using Mochizuki. But of course, you need some input. Questions about the sketch of the proof? Yes?
So if we are given pinned morphism and from which we construct the pi 1 morphism, which is point theoretic, and then we by Mochizuki we cover the morphism of schemes of curves. But how to ensure that this morphism coincides with the original morphism of étale topos?
Oh, well, this is a good
Not only finite étale, but étale.
You mean like a y coincides on k-bar value points? So I think this just follows from, you see this thing here, because I mean like I'm starting with my map of topoi gives me a map of fundamental groups, right? And then I mean Mochizuki gives me, if this is open, a map F of schemes, which is if I precompose with pi star, I mean like the pi 1, I get this map on up to conjugation by some geometric. Then you see that, well, this map, from this point theoretic map, I got a map of k-bar value points. And it agrees with the map of k-bar value points of topoi. And the map, when I get from Mochizuki, must do the same thing, because it's the same up to geometric conjugation as this map, right? So I'm done. Do you agree?
This is a so you mean the pinned morphism is only defined, so that the map between pinned morphism is faithfully represented in the set in the morphism of closed point.
Yeah.
Sorry, when you're not assuming something like the section conjecture, or
No.
you say like
I'm not assuming. I'm assuming that if this holds, I'm not assuming the section conjecture.
If you assume the second conjecture, then this point theoretic condition will become empty. Right?
Exactly. Yes. Yeah. So I'm not going to assume But so like that sections, like geometric sections, propagate nicely on the map of pin morphism of topoi.
So, but here you don't you consider the it is hyperbolic curve case, but anyway, so that if x8 to x8, this is some endomorphism of pinned topoi, then if this induces identity on k-bar rational points, then the original morphism of pinned topoi, this is identity also.
I see what you're saying. No, I mean I'm saying that if F comes from a map of the schemes, then if it's the identity on k-bar, I mean then you can show whether that map from the map of schemes into topoi, that's injective. But now you're asking a question whether the map of topoi is determined by this value on k-bar value points. I don't know. But we don't need that to show that that's not
free face we don't need.
Yeah, we don't need that. But I mean, like, it's I think that's a good question. But yeah, For general maps of topo, I don't know. If it comes from map of schemes, of course I know that.
For fullness, do we need
For the
fullness of the morphism?
you don't. I mean, you don't need it to show. So I see what you're saying. You want to say if for a few slides ago said if it's enough to consider what doesn't k-bar value points. But I see what you're saying. But it's not a problem here, and I'm happy to explain the proof later on.
I like to avoid the 3-4 hours of your.
Yeah, no, but I think it's a very good question. It's a very relevant question. I see the problem, but I think, yeah, but in short, it's fine. But I get, yeah. Further questions? Yeah. Okay. So this was the reduction. And the theorem which sticks to prove this openness is the following lemma, and this is a generalization of a result of Kreutz and Bolloch. So if you have a curve U, with smooth compactification X, let GU be geometric genus of X, let NU be the degree of the set of points of in the boundary, and let's this chi-U here is the Euler characteristic of U. The lemma you need is the following. So if U and V are geometrically connected smooth curves over Kummer faithful field K of characteristic 0, and this is non-trivial. So if this geometric fundamental group here is non-trivial, so pi1v k bars means the geometric fundamental group. If this is non-trivial, suppose then that psi is a point theoretic map over GK. Then if the Euler characteristic of V is less than or equal to -4GU minus 4NU, then the image of this map on k-bar value points is finite. So given this lemma, it's quite easy to show that theorem with sticks, which was here, that if I have such a map, either it's open or it's in a single decomposition group. So the sketch of the theorem is simply the following. So if psi is not open, you can write psi pi1 of U as the intersection of pi1 vi bar, and this vi here corresponds to pointed finite étale coverings vi to v with vi geometrically connected, and further the degree of vi to v becomes arbitrarily large. Because if this is either the image is either closed or open, this closed is an intersection of open subgroups of the arbitrarily large index. Then you can use the Riemann-Hurwitz formula. See that the Euler characteristic of vi becomes an arbitrarily large negative number because the degree becomes very large. So these bounds cannot hold when the vi are very large. And then further, these maps from pi1 of C to pi1 of vi, they're still point theoretic. So, but then you get some contradiction to the lemma I just gave previously. And this proves that the image of psi k bar is finite. And then you must use some further arguments to show that psi k bar is a point. And then it's a decomposition group. And now I guess I would want to sketch how to prove this lemma. That if you have this inequality, that the map of the k-bar value points is finite. So let's assume that U and V are projective, and let G and U and GV be the genus of U and V. Given a map from pi1 of U to pi1 of V, you can use abelian techniques so that this induces a group homomorphism between the k-barred value points of Jacobian of U to the k-barred value points of Jacobian of V. This is something you really need to construct using some abelian geometry. And it's not very hard, but still not some work needs to be done. And further, you can use this map between k-bar on k-bar value points of Jacobian. You get a commutative diagram as follows. So up here you have the k map on, this is the psi, the map on k-bar valid points induced by psi, point theoretic. And these are some inclusions onto Jacobian given by choosing some compatible base points. And this is the map which was induced by this guy here. So you have such as commutative square. And then further, you know that the map from the GU symmetric power into the Jacobian here, that's a dominant map. And this means, since U was assumed to be projective, that any element of the k-bar value point of Jacobian, it can be written as a sum of at most GU elements from U. I can take then this, precompose this image, this guy, the k-bar value points of Jacobian of U with psi. And this statement here and the compatibility of all the maps involved means that this image here is contained in the image of the map from the GUs, the symmetric power of V to the Jacobian of V. So by our assumptions on Euler characteristic, this map is not dominant. I can then take the Zariski closer B of this these k-bar value points of Jacobian of U. And this is then a proper subgroup here, simply by dimensional considerations. What I can then do is I can intersect this B with V k-bar, the k-bar value points of V. And since V is a curve, I have two options, right? Either it's a finite or it's all, everything. It's not everything, because if it was everything, we know that V k-bar generates this Jacobian here. But V would then also be contained in B, but B is also a proper subgroup. Those things cannot hold at the same time. So this intersection must be finite. But the image of this map from U to UK bar to V is contained in this intersection. So, yeah.
Are you using characteristic 0?
So you can make this work for characteristic P, but you need to have some assumption, but you can make this work for characteristic P.
The statement's going to change.
The statement's going to change, but you need to assume what's a Kummer faithful. So I'm using Kummer faithfulness here at certain parts. And for Kummer, you need to have a good definition of Kummer faithful fields in characteristic P. And with these things go through. You need some assumption. You need maybe to ask, well, maybe it needs to change some assumption, the fundamental group of pi U and pi V. For example,
I'm just worried about things like the fact that, right, if I take P1 minus many points, I can cover it.
Yes.
So that doesn't break the statement.
No, I think that's fine now. Yeah. So for fine, I mean, yeah, so it works fine still. And of course, this works for affine things as well. I mean, you use the generalized Jacobian. Yeah, so I mean, this is basically the sketch of how you prove the theorem. And I think like these all the questions like sort of like suggests that you want to try to attack problems of the following kind. So maybe the most pressing thing to try to answer now is ask, well, what happens over finite fields? I think that's completely open. I have some ideas, but they're not reach the target, so to say. But the corresponding thing you should ask over finite fields is the map from the perfection of X to the perfection of Y. It's the map into the corresponding maps of étale topo. Is that a bijective map? Seems plausible, maybe. And of course, the ambitious goal would be to say something about over spec Z. It's the map from Hom Z to XY for X and Y finite type into this map of topo. Is this bijective after localizing the Morse homomorphisms? So yeah, this seems doable. I have no idea about this. Okay, so that was all. So thank you very much.